Hello, my name is Ioannis Gialamas, and I am a postdoctoral researcher at the Laboratory of High Energy and Computational Physics in Tallinn, in Estonia. And the title of my talk is From Euclidean AdS Wormholes to an Inflating Universe, the Higgs Inflation Paradigm. And it's based on this paper, which was written in collaboration with Panos and Olga, and on this paper, which was also written in collaboration with Paul, and it will be online soon. So today we will explore some of the most fundamental questions in modern cosmology and theoretical physics. We will start by looking at inflation and the possibility that the Higgs potential is metastable, which could have important implications for the early universe. Next, we will discuss the challenges related to the initial conditions of the universe and how the no boundary proposal proposed by Hartle and Hawking has been suggested as a possible solution. I will then examine some of the issues associated with the no boundary proposal itself and how recent ideas involving Euclidean AdS wormholes may help to evade these problems. Finally, we will look at possible future directions and wrap up with a summary of the key points. As you know, in physical cosmology, inflation is the theory of exponential expansion of space in the early universe, occurring between 10 to the minus 36 and 10 to the minus 32 seconds after the Big Bang, and it was originally proposed as a solution to the horizon and flatness problems, but also provides a natural mechanism for the generation of the primordial perturbations. And these perturbations are also the seeds of the anisotropies we observe today in the cosmic microwave background in the CMB. One of the most famous models of inflation is the Higgs inflation model, where we assume the tree-level Higgs potential, as you see here, plus a non-minimal coupling between the scalar field and gravity and the rich scalar. And this non-minimal coupling is responsible for the plateau region of the potential. And you can easily see this if you do a while rescaling of the metric and go from the so-called Jordan frame to the Einstein frame. But if you go beyond tree level, if you go to one loop, there is a possibility, there is a possible metastability of the Higgs vacuum because at high energies, the Higgs coupling, the Higgs Cordy coupling, if you run it just within the standard model, in this figure you see the Higgs Cordy coupling lambda for the central measured values of the standard model. And as I said, if you run it just within the standard model, this lambda becomes negative and therefore opens the possibility of our universe to be metastable. But why lambda becomes negative? This can be easily observed if we see the one loop beta function of lambda. This contains the gauge couplings G, you see, the U1 is U2 gauge couplings, lambda itself, the Higgs Cordy coupling, and the Yukawa coupling YT. As you see, the Yukawa coupling, YT, gives a negative contribution to the beta function. As the top quark mass becomes larger, the Yukawa coupling becomes also larger, and due to its negative contribution to the beta function, the quartic coupling becomes negative at some scale, about 10 to the 10 GeV, or even higher. This is very sensitive to the choice of the standard model parameters. However, I should say that some recent analysis, I think 3 years ago, by both Atlas and CMS, seem to be giving a slightly different picture, pushing the top quark mass down. So let's assume that we are in the metastable regime. So the potential looks like this. It has a plateau region, maybe coming from a non-minimal coupling with gravity. And it has also a second negative minimum here, an AdS minimum. Of course, the precise shape of the potential at high energies depends on the UV completion of the theory. So we will remain agnostic about this. There are also other string or sushi realizations that can give us similar setups. The metastable Higgs is just a real-world realization. But in any case, in order to have a successful inflation, we need as initial condition to start high up in the hilltop of the potential. So even within the inflationary framework, several important questions remain open, particularly those concerning the initial conditions of inflation. For example, which processes determine the initial state that triggers inflation, or what sets the initial position high on the inflaton potential. In this talk, I will show you that we can achieve a semi-classical understanding of the birth of the universe, one that naturally leads to the standard Lorentzian inflationary evolution, starting high on the inflaton potential, even if the scalar field was initially trapped in a global AdS negative minimum. Harlan Hawking, almost 50 years ago, 40 something, attempt to address these fundamental questions, and to do so, they proposed the so-called no boundary proposal for the wave function of the universe. Before discussing it further, let's have a look at a few geometries. The key idea is that Euclidean geometries with Z2 reflection symmetry can be sliced in half to define initial tau equals t equals 0. Tau is the Euclidean time, t is the Lorentzian time. They can define initial states at tau equals t equals 0 of the Lorentzian evolution. So on the left figure here, you see the no boundary proposal, which is Euclidean de Sitter. On the right here, you see Euclidean AdS geometry that evolves into a crunching cosmology. And in the middle, you see a Euclidean AdS wormhole that initially shrinks, and then it locally expands near the throat of the wormhole, forming a shape that resembles the no boundary proposal. My focus in this talk will be on this middle configuration, the wine glass shaped half wormhole. So let's begin with a quick overview of the no boundary proposal using a simple example, empty de Sitter space. So consider a pure gravity with a cosmological constant that is Einstein-Hilbert axion plus lambda. This system admits an empty de Sitter solution. And in the Euclidean signature, the geometry is that of a four sphere, is the S4, while, as you see here, while in the Lorentzian signature, it becomes the familiar de Sitter hyperboloid. Now, in the Hartley-Hawking construction, the classical picture involves a complex metric built through a specific gluing procedure. One starts with the Euclidean S4, as you see here, slices it in half, and then attaches to it this half sphere. A Lorentzian attaches to this half sphere the Lorentzian de Sitter space-time. So you do this type of contour in the complex plane, and the resulting manifold is a smooth manifold. You can see details in this recent review by Lenners. However, the no-boundary proposal faces a significant challenge, a kind of hierarchy problem. You are already familiar with the usual cosmological constant problem. You know that this ratio is very, very large, 10 to the 120. Now, in the no-boundary proposal, in this context, the issue becomes exponentially worse. Because when one computes the probability associated with the universe's initial state, I will not go into technical details here, the result overwhelmingly favors an almost empty universe with the smallest possible value of the cosmological constant. In other words, the no-boundary measure is dominated by configurations with a minimal lambda. You can see this here directly. The probability is given by the exponential of minus the Euclidean axion, which is negative. Finally, the probability is given by something positive, which is has the potential in the denominator. And this problematic behavior originates from the fact that the on-cell axion of positively curved Euclidean de Sitter space is negative, which exponentially enhances its contribution and leads to this unrealistic preference for an empty and cold universe. Let's now turn to the wine glass AdS wormholes. For our purposes, their defining features are the following. The geometry is a wormhole with two Euclidean AdS boundaries at tau equals minus infinity and tau equals plus infinity. And the scale factor reaches a local maximum at tau equals 0. This is crucial because after analytic continuation to Lorentzian time, the scale factor begins to accelerate again, allowing the universe to enter an inflationary phase in the Lorentzian signature. You can easily see that in Euclidean time, the second derivative of the scale factor is negative. But after analytic continuation, to the Lorentzian time, the second derivative is positive as it should be in the beginning of inflection. Now, to construct such solutions, two key ingredients are required. First, we need the scalar potential that takes both positive and negative values, enabling the geometry to transition between AdS and inflationary regimes. And the second thing we need is a source of negative Euclidean energy to prevent the wormhole throat from collapsing. This negative energy effectively stabilizes the geometry and enables the characteristic wine glass shape I showed you before. Let me now move to a concrete model that realizes this idea. We start with the Einstein-Hilbert axion coupled to a scalar field, together with an additional component such as radiation, axions, or similar matter sector. And when we look for solutions with a spherically symmetric and homogeneous ansatz like this, we arrive at two key equations, the Einstein equation and the scalar field equation, the Klein-Gordon equation for the scalar field. The crucial point is the behavior of radiation in the Euclidean signature, because due to the relative minus sign between the electric and the magnetic components of the energy density, the Euclidean radiation energy density can effectively become negative. This is not the case in the Lorentzian signature because it is just E squared plus B squared. And this feature is essential. It provides precisely the type of negative Euclidean energy required to support the wormhole throat and allow these wine glass solutions to exist. Let me give you a few more details. In this setup, gravity naturally tends to make the scale factor contract. The geometry shrinks because of this factor, as you see here in the equation of motion, minus 1 over a squared. While actions or magnetic fluxes, due to the negative sign of the energy density, do the opposite, pushing the geometry to expand. And this competition is precisely why a negative Euclidean energy density is needed to balance the dynamics and allow the wormhole throat to form. So, in the Euclidean signature, the equation of motion for the scalar field describes a particle moving in the inverted potential, minus u, with an anti-friction term which is given by this. And so, as I mentioned earlier, the Euclidean geometry first shrinks and then re-expands. And this behavior causes the scalar field to first accelerate and eventually comes to rest at tau equals 0. And these are very good conditions for slow roll inflation. This turning point corresponds to the local maximum of the scale factor, as you see here, and essentially and that is essential for analytic continuation into an inflating Lorentzian universe. So the Euclidean trajectory as I said, effectively describes the nucleation of the universe at some initial value chi0 high up on the potential. And from this point, the system transitions to the Lorentzian time, where the scalar field naturally follows a slow roll trajectory down to the potential toward the vacuum, as you see here. Then you have standard inflation. And to realize this scenario, the early universe must initially be dominated by magnetic radiation or an axion-like component that provides the necessary negative Euclidean energy. And however, once inflation begins, both of these contributions are diluted exponentially to an enormous degree, leading behind the standard cosmology. So, what is the main advantage of this proposal over the traditional no-boundary construction by Hartle and Hawking? The key point is that when we evaluate the Euclidean wormhole on cell action, numerically or analytically, this is the Euclidean axion, the on-cell axion. We have also to add some the Gibbons-Hawking boundary term because our geometry has an AdS boundary, so we need our variational principle to be well defined, and some counter terms to cancel divergences. So if we compute this numerically or using some thin wall approximations, we generally find that it is positive. And this means the corresponding probability is now well defined. And crucially, it avoids the central problem of the no-boundary proposal. Instead of overwhelmingly favoring an almost empty universe with an extremely small cosmological constant, the wormhole scenario, the wine-glass wormhole scenario, predicts that the universe prefers to nucleate high on the inflaton potential. From there, it naturally transitions into the familiar cosmology we know, standard slow roll inflation, and so on. Within our model, we can also make an estimation of the value of primordial magnetic fields at the end of inflation and compare them with current experimental bounds. At the time tau equals t equals 0, where the Lorentzian evolution begins, the field is already positioned in the plateau region, allowing us to approximate the value of the potential at tau equals 0 with the value at the horizon crossing, the so-called pivot scale, 50 to 60 EFOLs before the end of inflation, depending on the model. So this is for the standard Higgs inflation. So using this, we can compute the value of the radiation energy density. We can put some bounds. And assuming that no fine-tuning takes place, but rather a small asymmetry between the magnitudes of the magnetic and electric components, the scale of the magnetic field density, which is magnetic field squared, at the beginning of inflation is 10 to the minus 11 m Planck to the 4. And now the interesting question is if these primordial magnetic fields can also be the seeds of possible galactic dynamo mechanisms that can sustain the currently observed magnetic fields. And the answer is no. because our magnetic fields um, at the end of inflation, after 50 to 60 folds of expansion, will be of the order of 0.1 to 1000 Gauss, while a galactic dynamo mechanism requires at least 10 to the 35 Gauss at the beginning of reheating and of inflation in order to survive uh, 10 to the minus 12 to 10 to the minus 22 Gauss today. So there is no possible mechanism of galactic dynamo using these magnetic fields. Finally, in this paper, which will be uploaded on arXiv soon, we are analyzing various Euclidean saddles in the gravitational path integral with asymptotic AdS boundary conditions in a class of Einstein scalar Maxwell models, like this type of disconnected and connected wormholes, which of course does not drive our universe to an initial inflationary period if we cut them at tau equals 0. But we are also looking on the Wine-glass type of wormholes and oscillating Wine-glass wormholes, which can arise if also the potential is a non-trivial periodic function taking both positive and negative values multiple times. And what we expect to obtain from this analysis is that the Wine-glass wormhole, what we want to obtain is that the Wine-glass wormholes dominate in the path integral, so they can give a convincing answer to the question about the initial conditions of the inflationary universe. This will come out soon. And currently, we are studying cosmological correlation functions in the Wine-glass wormhole geometries, where we do not assume the Bunch-Davies vacuum a priori, but instead the wave functional approach defines the vacuum state. And now let me conclude. As I told you, there is a new wave function of the universe constructed from the gravitational path integral with asymptotically Euclidean AdS boundary conditions. Semi-classically, it corresponds to a Euclidean AdS half wormhole geometry. And if the scale factor has a local maximum at the Z2 reflection surface, analytic continuation produces an expanding Lorentzian universe. The requirements for this realization are a scalar potential that spans both positive and negative values. And the second thing is an initial flux. For example, radiation or axions that must support the wormhole throat from collapsing. And finally, this proposal avoids some problems of the no boundary scenario, yielding a well-defined probability, which in this case is smaller than 1. Thank you very much.